Good day, my name is Ajayi Olasupo, and on behalf of the other authors, I'm presenting our paper titled Off-Peak Workload Allocation Models in Cloud Computing from the University of Western Cape, South Africa. This is the abstract, which gives a summary of the work. And in this work, this paper focuses on comparing five workload allocation algorithms consisting of economic, heuristic, and meta-heuristic models for the allocation of off-peak or batch workloads in cloud computing. Cloud computing is a computing paradigm that offers computing as a service rather than as a product, and it's a cost-effective way pay-as-you-go service to users. However, one of the major challenges of cloud computing is user satisfaction, especially service delays. These delays can result from network congestion or poor resource allocation schemes. Most cloud service providers usually prioritize premium or paying customers, and this is to the detriment of non-paying or free users. The focus of this work, therefore, is to obtain an effective allocation scheme for off-peak tasks that simultaneously balances cloud resources and user satisfaction. We start up with a review of related works, and we categorize related works into three major categories. Resource allocation based on nature-inspired meta-heuristics. These meta-heuristics include genetic algorithm, differential evolution, ant-colony optimization, particle sum optimization, and the likes. The objective of most of this work is to efficiently allocate cloud resources, to minimize allocation delays, and to ensure adherence to quality of service or service level agreements. The second category of workload or category of related works are those that use deterministic or greedy approaches. Here they assumed allocation of workload to be a bin packing problem, and they use a number of greedy algorithms such as first fit, best fit, binary fit, and the likes. Again, the objectives were mostly to ensure efficient resource utilization and to minimize workload delay. Finally, the third category of work were those that use economic models, and more specifically the stable roommate allocation or stable marriage allocation. And the objective here were to ensure quality of service and secondly ensure efficient resource utilization. For our work, we considered 5 algorithms from each of these different categories. The first is the economic model, the stable roommate allocation, which seeks to pair multiple roommates with contrasting objectives to rooms. Here we assume that the servers are the rooms and the user workloads are the objective is loaded in the rooms. Then we looked at genetic algorithm, which was proposed in reference 21 here. And then similarly, we used another meta-heuristic, which is differential evolution. Differential evolution is often considered as a rival or alternative to genetic algorithm, and hence it made sense to include it here. Finally, we looked at the most popular the most popular deterministic approaches, which are the best fit and first fit that have been used in literature. Our results, the models we used are: the objective was to maximize resource utilization, that is, to use to maximally utilize each server while ensuring that we are still below its utilization threshold, or the threshold in which it starts to become overwhelmed. Secondly, we also try to minimize the number of resources used. That is, even though we are maximizing each server's utilization, we also ensure that we use lower number of servers or least number of servers, and this directly translates to energy conservation, as 10 servers will consume less energy than, say, 20 or 30 servers. For our performance evaluation, we took 5 matrices. The first is allocation delay, which is a measure of how long the user has to wait before the processing of their submitted work begins. Here we consider it as the preprocessing time plus time taken to allocate the first task. And from our results, we can see that the greedy approaches perform the best, as they use the least time, while the meta-heuristic DEVA, which is the differential evolution, takes the most time, and this is because it requires time to converge before allocation begins. In terms of resource utilization, again, the greedy algorithms consume use the least number of physical machines at just above 60, compared to the meta-heuristic, which used almost double the number of resources to achieve the same number of tasks. The economic one was almost at par with the meta-heuristic. Similar results, of course, because number of resources is directly proportional to energy consumption, and so similar results are obtained for energy consumption also, as shown on the graph on the right hand side. In terms of quality of service, which is a measure of the adherence to preset user requirements, Deva and Gava perform the best as they are, even though they are slower, they perform the best as they ensure that quality of service are met. And this is what accounts for them being actually being slow, because they have to converge before the allocation begins. This is in sharp contrast to the grid algorithms, which do not take quality of service into consideration. Execution time is the time spent servicing the user's workload, and again, the grid algorithms perform the best here compared to the detriment or compared to the meta-heuristic approaches. We then finally have a summary table which shows that in all 5 categories, binary first descending perform the best. So we have deterministic model were best for speed and resource allocation, while the meta-heuristics were best for quality of service adherence. Finally, the economic model gave a balance or average performance across the matrices, the 5 matrices. Finally, we now decided to choose how to choose the best algorithm for each of the different user types. We mapped this table I showed previously to a numeric values, giving first a value of 5, second a value of 4, and then if you come last, or the worst performing algorithms are given a value of just 1. So here we now see that we chose 2 use cases. We chose a case of a cloud service provider and cloud service users, called cloud users. For the cloud service provider, again, these are the 5 matrices here. These 5 matrices compared to translate to allocation delay, resource utilization, energy conservation, quality of service, and execution time. For the cloud service provider, efficient resource utilization and conservation of adherence to quality of service are paramount, and that's why they're given higher values. However, for the cloud service user, he is not interested in resource utilization or energy conservation. To him, that's the cloud service provider's problem. But for him, he is more interested in, he or she is more interested in ensuring that his job is the quality of service, that he gets good service from the user, and that he's not excessively delayed, even though he is a non-paying customer. By the time we translate these to put it into a weighted formula, this on the left hand side we have for the cloud service provider, and the right hand side we have for the cloud service user. And these values are put here. Of course, each value translates to a weighted sum of 1. And from translation, by the time I multiply 5 by 0.5 and 0.4 by 4, multiply 0.15 by 4, etc., we get a value of 3.6. Similarly, on the right hand side, taking the weighted matrix into consideration, the highest value is obtained as 3.4 and obtained when using Gava. So for the cloud service provider, the first feed descending with a weighted sum of 3.6 is the best choice, as it gives you the best output, while best feed descending is a viable alternative. For the cloud users on the other hand, the genetic algorithm based virtual machine allocation is the best with a score of 3.4. As I'm sure his own objective is to ensure adherence to quality of service, which is what the Gava algorithm is able to achieve. However, viable alternatives are the first feed descending, best feed descending, and possibly stable remote allocation, as they also have values of 3.2, 3.1, and 3.0 respectively. In this work, we had considered 5 workload allocation models and compared their performance with respect to resource utilization, energy conservation, quality of service adherence, and allocation delay. The results showed that no particular model excelled in all categories, and that so as such, in order to do this, we came up with we also showed a weighted formula that's able to take user preferences into account, and was proposed to use to select the best model for specific user cases or use cases. Though this work had compared multiple allocation ways for diverse domain, the comparison was done in a simulated environment. In the future, we'll have to look at actually performing this experiment using actual test beds, such as the OpenStack framework. Similarly, a hybrid combination of these algorithms, leveraging on the strengths of each, could be explored for coming up with a hybrid combination that can leverage on the strength of each could be explored for future work. Here are some of our references. These are just some of the extracts, shorter references, and thank you for listening. So now we'll take any questions if you have any.